Okay, in this video we're going to give you some instructions to help you complete experiment 5 with titrations. In the first part of this experiment, we're going to be preparing a standard stock solution of our oxalic acid dihydrate. So H2C2O4 is known as oxalic acid. It is sold as the dihydrate, and it is a solid. And this is really helpful for preparing the standard because you can weigh out the solid really effectively on an analytical balance and get a lot of sig figs so that you know your concentration very well when you're doing your titration. So you'll start by weighing out this solid into a weighing vial. We use a weighing vial rather than a weigh boat because we can rinse out the weigh vial and do nice quantitative additions to our volumetric flask. We will add this solid to the volumetric flask. We're going to be using the 100 milliliter volumetric flask in this step so that we can make plenty of solution. And we're going to do this addition using our plastic funnel. That way we'll be able to ensure that all of the solid is transferred directly to the volumetric flask, and some of it might get stuck in the funnel, but that's not a problem because we're going to be rinsing our vial and our funnel with DI water to make sure that all of the solid is transferred. We will rinse the vial several times with DI water and add these rinses to the volumetric flask. And you can really add as much water as you need to make sure that that solid goes out of the funnel and into the volumetric flask. And then you'll fill the volumetric flask about halfway with your DI water. We're going to be using DI water for every step of this experiment. So anywhere where it says water, make sure that you're using the DI water from the bottles at your station. If you're looking at a volumetric flask, this is not the nicest picture of one, but halfway is about halfway on this bulb part. It doesn't really matter exactly where you're at. You just don't want to fill it because it makes it really hard to dissolve the solid. Then you'll swirl to dissolve the solid. You want to make sure you do this before it's full of water because otherwise the solid doesn't dissolve well. And then you'll fill your flask to just below the line that's marked on your volumetric flask. They're all marked slightly differently so that they can be really accurate, and you'll use your DI water to do that. Once you've done that, then you're going to get a plastic dropper and fill it with some of your distilled water, and you're going to add drops of water to get the meniscus to the line marked on the flask. And that's how you'll know that your solution is made well. If you go over, you will have to remake your solution. So make sure that you're careful with these additions. Once you're at the right spot, make sure you stopper it, hold the stopper in place, and you'll invert to mix. Usually 10 times is a good number, but you just want to make sure that your solution is uniform. Once you've made your solution, you want to calculate the concentration of the solution you made. So we're going to do a quick calculation to determine the concentration in units of molarity. So just a quick recap, molarity is moles of your solute, which is the oxalic acid over liters of solution. So let's start by taking the mass of our solid. Remember that this is the dihydrate, and so since it's the dihydrate, we have to include that in the molar mass that we use to calculate moles. So 1 mole of oxalic acid dihydrate has a mass of 126.068 grams. Since we're just interested in the oxalic acid, not the water molecules because they come off in the solution, when your solid is dissolved, we want to set up a mole ratio. And we know that there's 1 mole of the oxalic acid for every mole of the oxalic acid dihydrate. So from this we can calculate the moles, and we get 0.00114 0.130 moles of oxalic acid. And we'll divide this by the volume of that solution. So in our volumetric flask, we have 100 milliliters of solution, and we'll make sure to convert that number to liters. Then when you finish your calculation, you get 0.1130 molar oxalic acid. Notice because of the mass you weighed out and the use of a volumetric flask, you have 4 significant figures from the concentration in this calculation. Now in part B, we're going to prepare our glassware and the solutions for titration. So we'll start by adding water, a stir bar, and an indicator to a clean Erlenmeyer flask. I should have added another step for this, but at this point you should also rinse and fill your burette with acid from part A. So the solution you made in part A, your oxalic acid, is going to go in one of your burettes, the one marked acid. Once you've done that, then you can make sure to record the initial volume. Because you want to make sure that you know the volume before you add the acid from the burette to the Erlenmeyer. So you'll use your burette to add acid to the Erlenmeyer. You're going to add about 10 to 12 mils. It really doesn't matter how much you add. It really just matters that you record how much you added so that you can do your calculations appropriately when you get to that part. Then you'll add your unknown base to burette number 2. All of the techniques involved in performing these steps are written out in your laboratory manual. This is just a summary to help you think and plan in advance about what you'll be doing in lab. As I mentioned, you need to record the acid and base burette volumes accurately. The way to do that is you have to know how to read a burette. And unlike other glassware, when we read a burette, we actually read down. So the top number is always going to be a 0. The bottom number is something larger. The burettes we have in lab will be 25 mils. And you also can record 2 decimal places from your burette reading. And we're going to round to the nearest 0.05 milliliters. So that's another reason why we use burettes, is because we can get a lot of sig figs from them. So let's talk about how we read a burette. On our burette, the markings are every 0.1 milliliters. So if we start here at 0 and our meniscus is down here, we read this as 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and it's between 0.7 and 0.8, so we'll read this as 0.75 milliliters. Our final burette reading in this example has the meniscus between 49 and 50, specifically between 49.123 and 49.4, so we'll read this as 49.35 milliliters. So to know how much volume you dispensed, because that's always what we're interested in, we take our final burette reading minus our initial burette reading. And this tells us the volume dispensed. And this is really helpful because these are the numbers we're going to use in our titration calculation. So in this particular example, which is a little bit different than the burette you have in lab, but 49.35 milliliters minus 0.75 milliliters means we dispensed a heck of a lot. So I have to use a calculator for this because my mental math is not very strong. So 49.35 minus 0.75 gets us 48.6. But if your calculator shows 48.6, you have to add that 0 back in because by the rules of subtraction, And what we know about sig figs, we need to keep those decimal places. So we've got our volume dispensed, and this is similar to what you will do in the experiment after you've performed your titration. But you're going to make sure to record those initial burette volumes for both the acid and the base on your data sheet. Once you have the initial volumes recorded, you're going to do your titration, which will give you the final volumes. So this is the step that's going to tell you the final volume of your burette, or the final burette volume. So you're going to titrate with your base, which will be in your base burette, until the color of the solution is faint pink. If it's very pink, you'll need to add more acid and repeat the titration and write down a new final volume of acid. But you don't have to start it all the way over. You just want to make sure that it's faint pink. It only needs to stay faint pink for about 15 seconds. If you're not sure if your titration is finished, you can ask an instructor. Or you can write down the volume that you've added and then add one more drop to see if you go over. So you'll record the final volume of both your acid and your base burette. And then you'll set up your titration again and repeat your titration with a new sample of acid to get your data for trial 2. Once you've completed both titrations, then you can solve for the unknown concentration of your sodium hydroxide using a titration calculation. So in order to do this, we have to have the balanced equation for this process. So we know that the oxalic acid reacts with sodium hydroxide in a double displacement acid-base reaction. So we make sodium oxalate and water. Then we have to make sure our equation is balanced by putting a 2 in front of NaOH and a 2 in front of water. And now we do our calculation. So we know that we use 10 milliliters of our acid, which is our oxalic acid, and we're titrating 14.5 milliliters of base, NaOH. These are just some numbers that I came up with. You're going to use your own data here when you do it in lab. We also need to write down our molarity of the oxalic acid from part A. So mine was 0.1130 molar. Yours should be really similar to that, but not exactly the same. So to start our calculation, we're going to start with the volume and molarity of our known, which is the oxalic acid. And we need to convert this number to liters so that we can use our molarity, because what molarity tells us is that we have 1.1130 moles of our oxalic acid for every liter of solution. So we know that we use 10 mils or whatever volume you have for your titration of the acid, and we're going to use the molarity of that solution to get the number of moles. And once we know the moles of acid, we can use our balanced equation. So I'll make sure to color code it for you. So you can see that we have 2 moles of NaOH for every 1 mole, let's use orange, 1 mole of the oxalic acid. And we got that ratio from our balanced equation, which was why we wrote it. So your balanced equation should be the same as mine. So when I do this calculation, I get 0.00260, oops, sorry, that's a typo, 0.02260 moles of sodium hydroxide that were part of this titration, and the volume of the base that we used was 14.55 milliliters of the sodium hydroxide. Again, because molarity is moles per liter, I have to make sure to convert this quantity to liters. and I get a molarity of 0.1553 molar NaOH. Notice that because of the volumes and the concentrations, I can figure out this number to 4 significant figures. And then you would repeat the calculation for trial 2. And then take the average as indicated on your data sheet. Then in the next part, we're going to dilute the oxalic acid and see how that affects our titration. So the first part is preparing the diluted oxalic acid. You're going to refill your acid burette with solution A, and you will record the initial burette volume so that you know how much you're starting with. You're going to dispense about 15 milliliters of oxalic acid, this time into your 50 milliliter volumetric flask. So making sure that you're using the new volumetric flask, not the one we used in part A. It doesn't really matter if you get 15 milliliters less or more than that. All that matters is that you write down how much you actually took out by recording the final burette volume. So it doesn't so much matter that it's exactly 15, it matters that you record what the numbers are. And again, you'll make your solution. So you'll fill the volumetric flask halfway with your distilled water. You will swirl to mix it. It will be easy to mix because you're just mixing 2 solutions rather than dissolving a solid. You'll fill your flask to just below the line with your distilled water, and then you'll use a dropper to get the meniscus to the line marked on the flask. Again, this is your smaller flask, so the line might be different than where you saw it the first time. You'll stopper, hold, and invert this solution to mix it up. But before you do your titration, you need to calculate the concentration of your oxalic acid. And again, this time this is the diluted acid, and so it's going to have a lower concentration. To find a concentration of something, we use C1V1 equals C2V2. So it's telling us that C1 is our starting concentration, so this is the concentration of the acid from part A. The volume is how much you dispensed, so from step B in this process. C2 is the new concentration, that's what we're looking for, and V2 is the size of your volumetric flask that we're using. In this case, it's our 50 milliliter. So our C1 is what we calculated in part A, 0.1130 molar. The volume of it, I'll pretend I had exactly 15 milliliters. You will use whatever number you were able to dispense in this step. C2 is what we're looking for, and V2 is 50 milliliters. Notice that we have quite a few sig figs because it's a volumetric flask. So now we can do some algebra. We get C2 is equal to 0.03390 molar of my acid. Notice that I had to add that last 0 because I want to keep my 4 significant figures that I had from all of the measurements that I took. Now I can titrate. So I'm going to add water and indicator to my Erlenmeyer flask. Also make sure you put in your stir bar. And now, instead of having the acid from part A, I'm going to add the diluted acid to my acid burette. And I'm going to record the initial volume on my data sheet. Then I'll add some more unknown base to my burette. If it's full, don't worry about it, but if it's close to empty, then just add some more. And again, you will make sure to record the initial burette volume Once you've recorded those initial volumes, you can titrate just again as you did before until that faint pink color appears and persists for about 15 seconds. Then you will record the final burette volumes for both the acid and the base, so you know how much you dispensed. Notice that because the concentration of acid is lower after we diluted, you won't need as much sodium hydroxide to titrate the moles of acid that you have. So you should have fewer moles of acid this time, so you'll need less of your base to do the titration, but you will repeat your titration so you get 2 trials. So you'll set up your diluted acid again, repeat your titration, and then we're going to calculate the unknown base concentration again. So remember, we're still using that same oxalic acid, it just has a different concentration. And remember, our base, this time, this number should read 4.35, as it will on your sheet. Actually, I think your sheet has a typo as well, so make sure that you update this to read 4.35 milliliters instead of 2.25. I apologize for the typo. So, to do this calculation, we're going to start by writing that same balanced equation. We only changed the concentration of the oxalic acid. We did not change the reaction. We did not change the ratios in which the two things combine. So the equation remains the same. Also, in this part of the experiment, I apparently also used 10 milliliters of the acid. You might have used a little bit less or a little bit more. It doesn't really matter. Just make sure you're using your number here. Again, we're going to convert this to liters to make sure we have the correct volume. And now we're going to use the diluted molarity. Not the molarity from part A, but the diluted molarity. And again, I'll just write this kind of in bright color, your diluted concentration that we just calculated above in C1V1 equals C2V2. Then we'll do our mole ratio again, so I'll make sure to write this one color-coded as well for you. So we have that 2 moles of sodium hydroxide, and since we don't have a number in front of oxalic acid, we know that we have 1 mole of the oxalic acid that reacts. And now we can calculate the moles, and we get 0.00067804 sig figs moles of the sodium hydroxide. And we're going to divide it by the volume of the sodium hydroxide, which is 4.35 milliliters. Again, it was a typo in this part of the problem, so I made sure to update it for you. All right, now we have our moles and our volume, so we can find the molarity, and we get 0.160 molar NaOH. Notice though that now we had to switch to 3 significant figures because our volume of base only had 3. So notice the concentration that we got here for our sodium hydroxide is really similar to the concentration we had before. We just have fewer significant figures. And that's how you do the titration experiment.